Hello students, today we are going to learn a very important topic from our unit on alternating current, and that is the power factor. Now, I know many of you find this a bit confusing, but I promise you, by the end of this session, it will be so simple and clear that you'll be perfectly ready for any exam question on it. So, chalo, let's begin.
So, let me start by asking you a question. Have you ever wondered about this? Big factories, they use so much electricity. But sometimes they actually get a penalty on their bill for something called a bad power factor. Strange, isn't it? What could they possibly be doing wrong?
Well, the answer to that little mystery, and the key to understanding how power really works in AC circuits, is this one simple term, the power factor. And today, we are going to master it.
Now, before we jump into any scary-looking formulas from the textbook, let's understand the main idea with a very simple analogy. It's an analogy you will never, ever forget. Let's call it the beer mug analogy. Okay, so just imagine that the total electricity the power company supplies to a factory is like a full mug of beer. The whole thing, I mean the liquid beer and the foam on top, everything, that represents the total power the grid has to send. We call this the apparent power. You can think of it as the total effort the power company's making.
Now tell me, what do you really want from that mug? You want the liquid beer, of course. That's the part that's actually useful. In our analogy, this liquid beer is the real power. This is the good stuff, the useful power that does the actual work. It's what runs the motors, lights up the bulbs, and spins the fans. This is the power you're actually paying for to get work done, and we measure this in watts.
But every beer mug has some foam on top, right? It takes up space in the mug, you can't really drink it, it does no useful work at all. Well, this foam is our reactive power. In an AC circuit, this is a kind of power that just goes back and forth, sloshing around in the wires between the power source and the machine. It puts a load on the system, but it doesn't contribute to the final work done. It's just foam. So after all this, what exactly is the power factor? It's really simple now, isn't it? It's just the ratio of the useful part to the total part. It's the real power divided by the apparent power. In our analogy, it's simply how much beer you got compared to the size of the whole mug. It's basically a score, from 0 to 1, telling us how effectively the supplied electricity is being used.
And that brings us to the main goal. What would be a perfect mug of beer? All liquid, no foam, right? Similarly, the ideal electrical system has a power factor of 1. This means all the power being supplied is doing useful work. And now you know why those factories get fined. When they have too much foam, a low power factor, it means the electricity company has to supply a much bigger mug just to deliver the same amount of actual beer.
Okay, so the beer analogy is fantastic for understanding the concept, but for your exam, you need to use the language of physics. So how do we translate this into a proper formula? Let's look at the physics behind the foam. So here it is. This is the official formula for the average power, which is our real power, in any AC circuit. It says that power is the product of VRMS and IRMS. You remember those? The root mean square values of voltage and current. But it's multiplied by this extra special term, cos phi. So what is this cos phi doing here? Well, that term, cos phi, is the power factor. This is the physics behind our foam. The angle phi here, phi, is the phase difference between the voltage and the current waves. Think of it like a score for how well they are timed, or how in sync they are. If they are perfectly in sync, like in a resistor, phi is 0, and cos of 0 is 1. Perfect power. But if they are 90 degrees out of sync, like in a pure inductor or capacitor, phi is 90, and cos of 90 is 0. 0 useful power. Let's make this crystal clear with a tiny example. Let's say we have a circuit with an RMS voltage of 200 V and an RMS current of 5A. But because of some motors, maybe, the current is lagging behind the voltage by a phase angle of 60 degrees. So, step 1, what's the power factor? Simple, it's cos of 60 degrees, which is 0.5. Now, what's the useful real power? We just multiply everything, 200 times 5 times 0.5, which gives us 500 watts. But look, what's the apparent power? That's just V times I, which is 1,000 VA. See that? The grid is supplying 1,000 units of effort, but only 500 watts are actually doing useful work. The other half is just foam. All right, now for a very important section. Let's talk about a couple of silent killers. These are common mistakes that can silently steal marks from your paper in the exam, so please pay close attention.
The first big mistake is confusing power factor with efficiency. They are not the same thing at all. Efficiency is about energy lost to things like heat or friction in a machine. Power factor, on the other hand, is purely about the timing, the phase mismatch between voltage and current. You could have a theoretically perfect motor with zero friction, 100% efficient, but because it's an inductor, it will still have a poor power factor. Please remember, efficiency is about energy loss, power factor is about phase mismatch. The second silent killer is this term, wattless current. Many students think this means no current or zero current. This is a very dangerous misunderstanding. Wattless simply means that the current consumes no net power. It does no useful work, but the current itself can be very large. And this large current, when it flows through wires that have some resistance, will still produce heat because of the I²R effect. So wattless current can absolutely heat up and even burn out wires. It is definitely not harmless.
Okay, so let's bring this all together now. We'll see how this topic connects to things we've already learned, and then we'll quickly summarize the most critical points that you absolutely must remember for your exams.
Remember our topic of series LCR circuits? And that concept of impedance, Z, which was the total opposition to the current? Well, there's a beautiful direct connection here. The power factor, cos phi, is simply the ratio of the resistance, R, to the total impedance, Z. This is a very powerful and important formula to remember. It clearly shows us that when a circuit is purely resistive, Z equals R, and the power factor becomes 1. Perfect. So let's just do a final revision of the most important points for your exam. First, the two main formulas. Average power is P equals VI cos phi, and the power factor, cos phi, is equal to R by Z. Second, remember the special cases. The power factor is a perfect 1 for a pure resistor or a circuit at resonance, and it is 0 for a pure inductor or capacitor. And finally, please never forget, wattless current is not harmless current. It consumes no net power, but it is not zero current and can still heat your wires. Make sure these points are absolutely clear.
And I will just leave you with one final thought to think about. If this wattless current, the current that makes up the foam in our mug, does no useful work, but it can still heat up and burn out a real wire, is it truly harmless? This question really gets to the core of why power factor is so important in the real world. Think about it. That's all for today.